In the previous presentation, we showed that if we had a two-port device and we had knowledge of its impedance matrix, then we could insert it into a circuit. And if we could determine the equivalent circuit of the source at its input, and likewise the equivalent circuit of the load at its output, all the devices connected there, we could go through and determine the complex voltages and currents at each port. And from that, of course, determine the rate of energy flow into the input and also out of the output. Here are the results here. And again, I emphasize that if you ever use these equations for solving a problem, you've done something wrong. They're simply too ponderous, too difficult in terms of the complex algebra to do. And what we'll show here is there is in fact an easier way, at least I would argue a much easier way, of coming up with these answers. It also has the benefit that the analysis that leads us to this easier answer is one that provides greater insight into this two-port device. Not only are we trying to figure out the current and voltage at the port and the rate of energy flow across the port, we're trying to understand something about the device and how it works. And it turns out by this procedure that we'll talk about now, we can gain more insight into the device and how it works than what the transimpedance parameters by themselves might reveal to us. What we're going to do to make this simpler is to break it into two pieces. Go through and solve the problem for each port individually as opposed to simultaneously coupled the way the solutions on the previous page showed. So to do that, we're going to cut our circuit into two pieces. The source then will be in the left, the Thevenin's equivalent source. And then to the right of this port plane, we have this rather complex circuit. We have our two-port device with the transimpedance parameters, and connected to that two-port device, we have our load impedance. The important thing to recognize about this structure is now we have a one-port network. We cut the port in two pieces. We have a one-port network looking to the left. That's simply the Thevenin's equivalent source. And now we have a one-port network looking to the right. A one-port network that's made up of a two-port device that is terminated in an impedance ZL. I want you to think carefully about this result, because this is important to understand what we're doing, and sometimes students struggle with this result because they look at this circuit and they see a two-port device, but this is not a two-port device. Once we take our original two-port device and we connect something to its output port, in this case ZL, the input impedance of the remainder of the circuit, what we've done now is created a one-port device. There's only one port that we have here, and that is at the beginning. And so we can call the port voltage V1 and I1. That would be commensurate with how we defined it for the original two-port device. What happened to V1 or V2 and I2? Well, they're still there, but we really aren't declaring this a port of the two-port device, because the whole thing together now has become one single port, a one-port network. Well, one-port network, how do we characterize it? We characterize it with its input impedance. So the question we ask ourselves, what is the input impedance of this single-port device? What is the input impedance of this one-port device? Well, by definition, the input impedance is simply the ratio now of the complex voltage V1 to the complex current I1. The ratio of that will be constrained always by some complex number, which is Zn. Zn is a single complex number, an eigenvalue, which completely characterizes the entire one-port device. And that means it completely characterizes a device which is the original two-port device that has been connected to the load impedance ZL. Often students will tell me, gosh, V1 divided by I1, I know what that is. That is the definition of transimpedance parameter Z11. And so the input impedance of that one-port device, the original two-port device terminated in the load ZL, is simply equal to Z11. So this is the result. We get quite a bit here. I should say this result here is oftentimes what I am told. But remember, Z11, once again, is not the voltage V1 divided by the current I1. it is the voltage V1 divided by the current I1 only in the condition that all other currents, specifically in this case I2, is equal to 0. In other words, V1 over I1 will be equal to Z11 when port 2 is connected to an open circuit. But of course, port 2 is not connected to an open circuit. We've connected port 2 to our load ZL. Generally speaking, that's not going to be an open circuit. It can be any arbitrary impedance. And so we simply can't go through and say that the input impedance is equal to Z11. It is equal to V1 over I1, but remember we showed before that is equal to this result. Only when I2 is equal to 0 does this term go to 0, and V1 over I1 will be numerically equal to the transimpedance parameter Z11. But generally speaking, I2 is not equal to 0 because ZL is not an open circuit. And so the question, what is the input impedance? Once again, we know it is not equal to transimpedance parameter Z11. In addition to the algebraic proof that the input impedance, when a two-port device is terminated in some load, that input impedance is not equal simply to the transimpedance parameter Z11. Again, in the previous page, we showed that's mathematically not the case. We also want to make sure that we understand that physically that cannot be the case. It simply doesn't pass the smell test. It's important to understand that the input impedance of a single-port device is a equivalent circuit to the entire one-port device. It says something about every element of that one-port device, everything inside the blue box that consists of that single-port device. And so we look at our one-port device here, and how do we parameterize it? Well, there are 5 complex numbers that determine the single-port device here. First of all, the first 4 transimpedance parameters of the original 2-port device, and then finally a 5th parameter, which is the impedance of the load, the input impedance of an equivalent circuit that we terminate the output with. So there are 5 complex numbers which make up this one-port device. And if the input impedance characterizes completely that one-port device, then it must be dependent on all 5 of those parameters. Again, that's a theme throughout, that every element of a circuit typically will be important with determining any characteristic of that circuit, and that's certainly true with input impedance. And so we'd expect the input impedance of this single port device here to be dependent on 5 parameters. To be dependent on Z11 for sure, but in addition to Z11, it should also be dependent on Z22 and Z21 and Z12, and finally ZL. Sometimes students leave out ZL. They think physically, well, that can't be part of the result that we get for input impedance, because they tend to think input impedance is something that describes the one-port circuit right here at the beginning. It's at the input. If I were to open the door of the circuit, the one-port device here, and I stepped inside, what's the first thing that I would see? Whatever that impedance is, that's the input impedance. It's the initial impedance we encounter. And again, that could not be more untrue. The input impedance, again, is a characteristic of the entire thing, from the input all the way to the back end. It has to include everything. It's not simply a statement of the first part of the circuit. It is an equivalent circuit for the entire circuit altogether. So make sure that you understand the input impedance is going to depend, generally speaking, on every parameter that is required to describe the entire circuit, and therefore Zn is equal to Z11 simply doesn't pass the sanity check. How then do we specifically determine the value of Zn? Well, just like any other circuit analysis that we've done before, if we know all the equations that describe all the elements in our circuit, we can go through and do the algebra and find the result that we desire. In this case for Zn, what are we looking for? Well, we want to know what the value of V1 is, in this case in terms of I1. All right, we can't solve for a numeric value of V1. We want to know V1 in terms of current I1. And so we take our 3 equations, 2 from the original 2-port device, third equation, which is the equation for that load impedance. And again, note the minus sign here. We've written this in terms of the definition of I2, which is positive when coming out of ZL, and that's why the minus sign. is there. We combine these three equations and try to solve for V1 in terms of I1. And once we do that, we can divide out I1, and this becomes the result that we get. This is the value of the input impedance when our two-port device is terminated in some arbitrary load ZL. We, of course, want to immediately look at our result and verify that it passes all of our sanity checks. And if we look carefully, it satisfies the three that we typically go through: is the type of value on each side of the equation similar, real equal to real, or complex equal to complex, or even imaginary equal to imaginary. In this case, all of our values, both on the right and left, are complex. They'll have a real and imaginary part. Does it pass dimensional analysis? Well, Zn has units of ohms, and if we look at that, Z1 is ohms, and then we get ohms squared divided by ohms, and so we get ohms likewise for the second term impedance there. So dimensionality, it works out. The final thing we look for is, does the result depend on all the parameters that it should depend on? And we just previously gave the argument that the input impedance should depend on all 5 parameters that parameterize our circuit, all the 4 transimpedance parameters, in addition then to the value of ZL. Well, let's go through and count them. 1, 2, 3, 4, 5. They do. So this makes sense. Again, if this wasn't the case and only depended on 4 of them, it would make us suspicious. But it can happen, but usually it does not. So we feel pretty good. Now, there's another sanity check that we can apply, and this is a very powerful tool whenever you get a result. You ask yourself, is there some condition for which I know what the answer should be? This is the general result, of course, that we give here for an arbitrary value of ZL. But the question we might ask is, do I know what Zn should be for a specific value of ZL? And if I do, I might validate it mathematically to see if I get that answer. If I know that, Zn should go to 0 and ZL goes to, some value, well, put that in there and see if you get it. Generally speaking, in these types of sanity checks, we take a value and we send it to 0 or we send it to infinity. And in that case, we know what the answer should be, and we check mathematically to see if that is the correct result. In this case, we're going to go through and set the value of ZL, the load impedance, equal to a value of infinity. What is ZL equal to infinity? Well, that's an open circuit. In other words, if the load impedance is an open circuit, what should the input impedance be? Well, we've already just discussed this a couple of pages ago. We said that the input impedance, Zn, would be equal to Z11 if the load were infinity. In the unlikely case the load were an open circuit, only then would the input impedance be equal to Z11. Well, let's see if that's mathematically the case. If that is true, then our math should bear that out and provide us with yet another sanity check in our result. And so we take the input impedance and we evaluate it when the load is an open circuit. ZL is equal to infinity. And so we find the second term goes to 0, and we're left exactly with Z11. Our sanity check is passed. The input impedance is equal to Z11 only in the condition that ZL is equal to infinity. We know that to be true, and mathematically our result verifies this. So it's passed a 4th sanity check. We're feeling pretty good that this result is correct. So let's go ahead and finish up what we were attempting to do in the first place. And if you recall, that was to determine the current and voltage at port 1 of our circuit. Instead of going and doing a coupled problem where we simultaneously determine V1 and V2 and I1 and I2, we went through and said, let's just do the first port first. And what we did was replace then everything to the right of that first port plane, the 2-port device terminated in a load. We replaced it then with its equivalent circuit. And this is the input impedance now to this circuit, which is everything to the right of this plane. What we've done is got back to our original simple circuit, a source directly connected to the load. What is the load in this case? It is the input impedance of some useful circuit. In this case, not the input impedance of the blue box all the way on the right, but the combination of this 2-port device and the blue box all the way to the right. We look at this, and this gives us some insight into one of the reasons that we like to perform this procedure of determining the input impedance. What we really can do is look at this and interpret it as an impedance transform. We started out with a load ZL, and we connected a two-port device to that load ZL. And now, instead of having an input impedance, which is whatever ZL is or was, now we have a new impedance, which is Zin. ZL might have been 26 minus J30, and then Zin could be, 45 plus J17, for example. ZL is different than Zin. ZL has been transformed to Zin by the two-port device inserted here. That's one way of interpreting what has happened. And this is helpful to us because this impedance transformation will tell us oftentimes something about this two-port device, how it works, the characteristics, how it might be useful to us. And so, again, we look at this original circuit and we say, oh, we're going to interpret the two-port device as an impedance transformer, changing ZL into a new impedance, Zn, which characterizes everything to the left of the port plane. Now we have a simple circuit that we can analyze. We've done this before. I1 simply is equal to this by Ohm's law, and V1 is simply equal to this by voltage division. Now this looks so much simpler than what we had originally for our results for I1 and V1. Remember all those impedances that are in there. It's a little misleading because, of course, here we have to know the value of Zn, and that's may be not trivial to determine. In the previous page, we had an equation for finding Zn from Z11, Z22, Z21, Z12, all the transimpedance parameters in addition to the load. We'll find in a lot of useful circuits, it's not as complex to determine what that input impedance should be. In fact, devices are designed to provide a certain input impedance. That is part of what the usefulness of the device is, and that's certainly lectures for much later. But once you know the input impedance, how a two-port device has transformed a specific load into the input impedance, then determining the current and voltage at that port 1 becomes straightforward. And of course, once you find the current and voltage, you can determine the rate of energy flow, at what rate energy is coming out of the source and therefore coming into the input impedance, absorbed by the input impedance, absorbed by this load in this case. In this case, we mean if it's absorbed by this, it's absorbed by all the circuit that it represents. Somewhere in the original circuit, energy is absorbed by a rate that we can determine from I1 and V1. Frequently, students get nervous when it comes to calculating the value of V1 or I1 because I provided them with two different equations. On the one hand, we have a value for I1 and V1, which involves all the transimpedance parameters, all four of them, plus the value of ZL. That's the more longer, complex-looking equation, the one I told you never to use. And then there's a second equation I provided on the previous page, which is much simpler. However, it involves the value of Zn in the calculation. And students are like, which one should I use? I need to know which one because, they look completely different, so I'm sure they'll give me a completely different answer. And if I don't know which is the correct equation, then I'm going to get the wrong answer. Well, I'm trying to show here on this page that either one, the two are exactly equivalent. It's just two ways of doing the same thing. If we take the value of Zn, which we previously concluded in this lecture, and we insert it into the equations for V1 and I1 on the previous page, the ones that involve Zn, and we do a little algebra, what we find is I1 and V1 can be written then in terms of the transimpedance parameters and ZL, and these are precisely the same equations that we came up with when we solved the general circuit when we for both V1 and V2 and I1 and I2. And so it passes the sanity check. And again, what we're saying here is it's two ways of doing the same thing. You will get exactly the same answer, whether you solve the problem as a coupled problem, simultaneously determining I1 and V1 and V2 and I2, or we go through and we look at it as an impedance transformer. We take the load impedance, we transform it by the two-port device into a new input impedance, and then use our simple circuit then to determine V1 and I1. Get the same answer in either case. However, For this class, we'll find it's always much easier to do the latter procedure, to do an impedance transformation. Not only is it easier to transform the impedance into a new input impedance and then simply do the source load calculation, the transformation of the impedance will tell us a lot about that two-port device, its characteristics, and its usefulness.